Math 2414, integration by parts. If you happen to be watching this video and you're taking my class, then this is Chapter 6, Section 1 out of our textbook. And if you happen to be watching this video and you're not taking my class, this is still Chapter 6, Section 1 out of Essential Calculus Early Transcendentals, 2nd edition by James Stewart. Integration by parts. The previous series of videos reviewed a lot of topics from Calculus 1. Derivative rules, the fundamental theorem of calculus, some integration rules, and integration by substitution. But integration by substitution is just one of multiple integration techniques. This course technically begins with techniques of integration, which is what Chapter 6 is. So the first technique of integration we're going to learn, after substitution of course, is called integration by parts. Now, what's the genesis of this? In other words, what's the motivation behind the formula that I'm going to show you when the time is right? The motivation behind integration by parts is actually the product rule. So you can think of this as the product rule in reverse. Sort of. Now, what do I mean by sort of? Well, if we start with the product rule, we could say something like the derivative with respect to x of the product of two functions, we'll say f of x times g of x, is equal to the derivative of the first, and let's use prime notation over here. The derivative of the first, so f prime, times the second, g of x, plus the first, f of x, times the second, g prime of x. Well, what would happen if we took the product rule and we integrated it with respect to x? Integral dx, integral dx. On the left side, essentially you have the integral of the derivative, so it would restore the original integrand up to a constant of integration. So we would get back what we started with, because again, we're just integrating the derivative. Those are inverse operators, if you will. But on the right side, it's not as straightforward. We really can't integrate, we can integrate a sum term by term, which means we can, quote unquote, distribute the integral to the first half of the addition problem and the second half of the addition problem. But integrals do not distribute across multiplication, meaning that we can't just integrate each half of this product. We have to leave this as a single integral. So if you think of it as the product rule in reverse, it would look like this, but what good does this really do us as an integration technique? An integration technique is supposed to say, if you have an integral that looks like this, this is what you should try to do to it. So we have two integrals, and they're lumped together on one side. But what if we isolated one of these integrals? For example, what if we isolated this one by subtracting this from both sides? In fact, let's go ahead and write that move from an algebra perspective. Subtract the integral of f prime of x, g of x dx from the left. Subtract the integral of f prime of x, gx dx from the right. Of course, these would cancel. And then we end up getting that integral isolated. And because this is going to be our quote-unquote rule, I'm going to start writing this by writing this integral. The integral of f of x, g prime of x dx is equal to, and then on this side we have the product of f of x and g of x minus the integral, and I'm going to reverse the order of this product. I'm going to write the g of x first. It really doesn't matter. And then the f prime of x second. But in most books, when they give you what's called integration by parts, which has two integrals in it, each one has a function and a differentiated function. The differentiated function is typically written second, although it's not absolutely necessary. And this thing that I'm putting in a box is what's called integration by parts. The word parts in the phrase integration by parts means part of a multiplication problem, also known as a factor. So this integral actually has three parts, three factors. It's got the f of x, it's got the g prime of x, and it's even got the dx. And this integral, of course, has three parts also. This product has two parts, if you will. But as an integration technique, does it really tell us how to integrate something that looks like this, and how do we even spot something that looks like this? And the answer is not really. Integration by parts is a technique that doesn't do an integral. It's a technique that changes it to a different integral in the hopes that the new integral is workable. In other words, if we can't do this integral, maybe we can do this one. And we're going to see several examples of how to spot which part is which and how to set up the change according to integration by parts. But the flow of all of it's going to be pretty much the same. You have an integral and you want to view it basically as two parts. A function on its own and the derivative of some other function as another factor. And if you can identify who's the function and who's the differentiated function, if you can recover the differentiated function's original function, in other words, if you look at part of the integrand and say, hey, you're the derivative of something, and call that something g, and if we can take the original function that wasn't differentiated and find its derivative, that's straightforward, then we can disassemble this integral and rearrange it into this expression in the hopes that we can do this integral. Before I wrap up this video, I do want to show you a cleaner way of representing integration by parts, because although what's in this rectangle is absolutely correct, there's a more standard way of writing it using fewer letters. The standard way of writing it is to, it kind of looks like a substitution, is to call this function u, or one of the functions u, and the other function v. And you got to be careful that your u's and v's don't start looking alike. Well, if we call this function u and this function v, then this f of x is also u, but what would g prime of x dx be? Well, it would be the derivative of this. It would be dv. And similarly, on the other side in this integral, we call the g function v, so we'll put a v here. But f prime of x dx is just the derivative of u, so du. So if we write this expression, this equation, using u's and v's instead of f of x and g of x and their derivative notations, we could say that integration by parts is the integral of u dv is equal to uv minus the integral of v du. Now, if you're just trying to commit stuff to memory as opposed to understanding what's going on, then this is what you should have memorized. But if you know that it's just the product rule integrated and rearranged a little bit, then you don't have to really memorize this. It will just jump out at you all the time. All right, in the rest of the videos, 1, 2, 3, 4, 5, I got about 7 more videos. I'm just going to be demonstrating a lot of examples, emphasizing how to recognize when to try integration by parts, how to identify who the u and the v are, and then once you've made those identifications, transforming the integral into a new expression in the hopes that you can actually complete this integral. Just remember, in the phrase integration by parts, parts means parts of multiplication problems, aka factors.